Okay, so up to this point, we've been laying the groundwork for the real payoff that gives us our real functional programming characteristics that we're looking for. We talked about functional interfaces, and by using the default keyword, you got to remember one of the things the Java changes have to take into account is until they make the decision, which they may never make, to break backward compatibility, they have to be backward compatible back to Java 1.0 of 1996. So they couldn't just make up new keywords, because how many programs might exist out there with those keywords as variables or method names or something. So they drew on the default keyword and they used that in the functional interface. And so by declaring concrete implementation of a method in an interface and making it default, then they were able to give us a functional interface with concrete behavior. Then we saw lambda expressions allow us to take what otherwise would have been a nice addition, but used in an anonymous interclass way would have not made our code more fluent. It would have made our code less fluent by having to declare anonymous interclasses of these functional interface types. It would have been really tedious, and we probably would not have really enjoyed doing that. So by introducing lambda expressions, we now, the compiler treats them as the functional interface type, but and does a lot of type inference for us now. So Java is still a strongly typed language, but the compiler looks around at the generics that have been declared and what the collection is and whatever, and it infers what the types are for these lambda expressions, thus simplifying the lambda expressions, or allowing us to simplify them to not include type information. And then they added method and constructor references, which further allow us to get down to the nitty-gritty of just saying what we want the program to do, not how to do it. So instead of saying, I have this instance and I want you to invoke this method, you could just say, hey, there's this method on this class for every element in this collection, invoke it. It's a little cleaner and a little nicer. The constructor reference, I think is okay, but I'm not going to spend a lot of time trying to figure out how to use that, because I don't see the great payoff there that I do with, say, method references or lambda expressions. But all of that has been foundational to get us to this place, which are strings. We're going to first talk about an imperative approach, something I guarantee you the style of programming you'll recognize from the get-go. And then we're going to do the same thing with a functional approach, and we're going to see how the code improves. Code, it said, is read 9, 10, 11 times more than it's written. So you might spend an hour writing a block of code, but over the course of the life of that little bit of code, you might spend 10 hours or 12 hours or 15 hours of a maintenance person reading through there trying to figure out if the bug is related to what you're doing in that piece of code. So having readable code is not just an aesthetic nicety, it really does go to building systems that are easier to maintain. And then we're going to have some interesting notes about streams and see a full example. So here's the imperative approach. And if you have seen something like this before, I'm going to ask you to raise your hands. I have this method called calculate taxable total. It's going to return big decimal. I start off by initializing a variable called taxable total to 0. And then I go through my line items. So this is all orders have line items, right? And I ask if the line item is taxable, then calculate the total for the line item. And, a total for a line item is quantity times the price for the line item. And then add that total to the taxable total. And then assign that taxable to the new thing that we got, because remember the add method on big decimal, big decimals don't mutate, so it makes a new big decimal, and I assign that new one back to the taxable total. And when I'm all done with all of this, I return the taxable total. Anybody ever see code like that in your stuff? Raise your hand if you've written code like that. Because we all have. It's all very imperative, right? It's just tell the computer how to do things. Tell it that we need to declare immutable. Tell it how you want to iterate. Tell it how you want to filter. decimals aren't mutable, but we're actually replacing the reference with a new reference. So in a sense, it's mutation. And then finally, we yield an answer. Now, someone comes along and says, oh, but there's 500,000 line items. You need to do that concurrently. Wow, my filtering's all like mixed in there, and it's all like jumbled together in one place. It's going to be really hard to kind of pull out the parts that I want to do concurrently and pull out the parts that need to be assembled into the whole. So what's wrong here? Well, the love of mutation is the root of all evil. If we didn't have mutation, and mutation comes about, if you go to the ArchConf and you hear Neil Ford talk at these there, he invariably will mention that mutation comes, the reason we mutate variables in Java is that when Java came along in 1996, we were very highly resource constrained, right? A 1 gigabyte hard drive in 1996 was probably $2,000, right? Memory, more than 512 megs of memory was probably costing you thousands and thousands of dollars. So what we did is Java was designed to reuse memory and reuse storage because it was so expensive. Today, I carry around 32 gigs on my phone and 64 gigs on my tablet, and I think nothing of it. But in 1996, you'd pay $10 million for 64 gigs of RAM. So we were highly resource constrained, and so we mutated everything so we could reuse that memory. And that has led to all kinds of concurrency problems. We buried the filtering logic inside the loop. So if I wanted to do this concurrently, I have to kind of reach in there and figure out how to extract that so I can handle it, maybe filter across 50,000 filters, for instance. We're telling the program how to iterate. So then the computers laugh at us after we go home because we're telling it, hey, I'm creating a for loop and loop through these items. And it's like, I know how to do that. You guys are fools for writing that code. But there we are. Even though some of the items are taxable, we loop all the way through the loop. Now, this might be unavoidable, but what if all I wanted was the first taxable item? Like, all I really want to know, is there a taxable item? So find me the first one. If I get something back, then there must be taxable items, so now I treat it in a different way. So we end up looping all the way through. Here's the functional approach. I get my collection. I call the string method, which gives me a new thing, a new Java 8 name, which is a string. And then on that string, I have a filter, map, and a reduce method. The filter says, use this method reference that's on line item. There's a is taxable method, same method I was calling before. That's this method, right? That's right there. So the line item has this method, so I'm using the method reference here, so I don't have to declare variables. So with method references, the code gets just a little cleaner than it would have been if I used, say, a land expression. A map here is not like a Java util map. This is like a mathematical map. I have elements that live in one domain, and I want to transform them to be elements in a different domain. This map says, you start off with a line item, calculate the total, which produces a big decimal, and then what I end up with, basically what gets fed into the map after the filter is, the filter produces a collection of line items, the map transforms that collection of line items into a collection of big decimals. Then the reduce is, start with a 0 value, and then call add on each of the elements, and, continually build up that total. That's those 3 lines are exactly the same 3 lines, or exactly the same behavior as these lines over here, except I didn't have to tell the computer how to iterate. I didn't produce a single mutable variable. I didn't produce a single iteration. Like, does it use a for loop under the covers, or does it just get an iterable and iterate through, or does it use a while loop, or does it use some fancy new thing only known to Java 8? I have no idea. How much do I care? Not a bit. I want to tell it what to do. Filter this line items, whether they're taxable. Take what is taxable, convert them from line items into big decimals, and then sum up those big decimals. I tell the computer what I want done, not how to do it. That way they don't laugh at me when I go home at night. So what's going on here? None of our variables mutated. We said we want to filter using a method reference. We don't even have to use a lambda expression with variables and all that. Nothing. We just use a method reference. We transformed our line item to big decimal using calculate total. And now we're telling the program to iterate, not how to iterate. When we total the big decimals in the collection, and initializing equals 0. Since only some of the items are taxable, up to the reduce, those two operations are lazy. This is important, particularly if you are like looking for the first one. Okay? This example back here, I would have to loop through the whole list, and then I would have to put in like a break or something to get out after the first one. Here I could put find first instead of reduce. I could say find me the first one that's greater than 500 or whatever the requirement was, and then it would stop at that point. So let's see what this actually works on with the lazy evaluation example. A little contrived, I will admit. So I have this value called in the zone, and in the zone is just a number. And then my filtering behavior is when the value that I'm looking at is greater than in the zone minus 5. So once I get to up to 5, within 5 of being in the zone, and the value is divisible by 5, it passes the filter. And if it passes the filter, I say it's included. If it was skipped, I say skip. Then on the main, I just initialize an int to get into in the zone. And then I get notice this is an int stream. This is the new Java 8 thing. And I say, give me a stream of values from 1 to 100 integers. And the box defines it on the ends. So I call, and then I say values, filter, and map. Filter this based on the filter method. Notice I'm using a method reference here to my static method, and a map I'm using method reference here to the static method map. So I don't need lambda expressions. Now I have a couple of lines of output, and then I'm looking for the find first. So I want to find the first value that is in the zone that is divisible by 5. That's fundamentally what I'm doing there. And then I square that. The mapping is actually just squaring the value, so it's transforming it from what it was to the square of what it was. So what do we get with that? In the zone, I come in at 24. Look at this. What does this comment tell you? The fact that we get this comment before I got these comments. That it was lazily evaluated. I got these comments before I got those comments. Right? Which means the filtering and the mapping did not occur until the compiler hit this termination, find first. And then it went back and said, how can I smartly optimize the filtering and the mapping so I only filter and map the number that I need, right? And so I get that, it hits termination, and it goes 1 to 20. Now I get into the zone at 19, 20 gets included, but I'm asking for find first. So it stops, and then it maps it to the square of 20. So it didn't go all the way through 100, even though I asked, back here, I asked for a range closed of 1 to 100. But it found the first one, and it stopped the processing. But it didn't even start the processing, the filtering and mapping, until it hit the find first method. So this is the power of lazy evaluation. Now here's a more complex example, slightly so. I changed the zone a little bit here. I have two filters. Filter 1 is, the zone is minus 5, in the zone minus 5, and in the zone plus 5. And then filter 2 is the number divisible by 3. And then the termination is find first. Okay? Now notice there's another one here called reduce. So let's look at this. Here's the method. Again, when I call values, I say filter on the first filter, then filter again on the second filter, then do the map to transform them into the squares, and here's my termination to really drive home the point that this is the terminating behavior. And then I output some squares. So what do we get here? Well, here in in the zone value is 21. 21 minus 5 is 16. So 1 to 15 is skipped. 16 gets included by filter 1, but because it's not divisible by 3, it's skipped. 17 is included in the first filter, but it's also not divisible by 3, so it's skipped by the second filter. 18 is included because it's in the zone, and it's divisible by 3, so it passes the second filter. Since I was doing a find first, it transforms 18 into the square 324. So notice I can stack filters together, and each filter works on the results of the prior filter. Now, here, what I did was I used the reduce method. Now the reduce is a summation. Well, it has to go all the way through because it doesn't know like when I'm going to run out of numbers. It's not smart enough to know that I'm outside the zone and that it should stop. So I keep going up to 15, skip, and 16 included the skip on the second, same thing here. 18 is included. Now I keep going. 19, 20, 21 is included on both. Keep going. And oh, by the way, the code back here, you might not have noticed I didn't point it out. I only went to 25 because I didn't want to 100 of these. And so now I ended up with 3 values, 18, 21, and 24, that went through the mapping function. And so the sum of those squares is that. So I can stack filters, and I don't actually start processing the filtering and the mapping until I hit that reduce method. And you see that comment being at the top. Any questions about this lazy evaluation? You can really parlay that to avoid unnecessarily processing through thousands of records when all you really care about is like the first one, right? Okay. Here's a full functional demo. The line item is what we talked about. It's, it has a reference to its order, and I created with that constructor. Here's that calculate total. I have a little sleepy function here because I want to introduce it to time delay. And then the way I calculate the total is I take the price multiplied by the quantity, and then is taxable. I just return whether it's a taxable item or not. An order has line items, so list the line items here. I then can calculate a taxable total. Now this is the example of an imperative way. This is that imperative code here where I set a variable, I move, I mutated, I filtered inside the loop, etc. Same thing. Look what I have to do for the taxable and non-taxable. That code looks almost identical because it is almost identical. It's just this operator right here. But because the filter was inside of my method, and let's say I'm a really junior developer, I just copy and paste this one, and I put it in here, I put the bang operator, and I call it a day. I really should refactor the filtering out to a common method and all that, but I didn't do that. So I have really 2 identical kind of methods. And then I have the calculating of the tax and the calculating of the total. Well, here's an order factory. There's really nothing interesting here. I make some line items, add them to the order. The only sort of sad thing here is that alcohol is taxable. And other than that, I can't really say much about that. I am using the local date here, so that's another handy reference in the date. I do use methods other than now. You can get the year off, you can get the, if it's a date, you get the year, the month, and the date off. I mean, how convenient is that? And we've learned all that in JavaFX. Don't have to use calendars. So let's test this. I have a main method. I start my time, and I create the order, which runs through the order factory. And then I run out a non-taxable total, a taxable total, what the tax is, the order total. And then I output the final time. And this is the results. Nothing particularly interesting here other than it took 1.61 seconds to do it with the sleep delay that I put in there. So here is a more functional style of that same order. All right? I went ahead and cheated and just extended order because I need all the same fields. And here's how I do the calculate taxable total. I get a string, so I have a method here called getString, which is given the line items device here is all I needed to do to calculate taxable total. How about to calculate non-taxable total? Well, I get the string, I filter, and now notice instead of using this method reference, there's two ways I could go. I could create a method called is non-taxable, and then do the reverse analysis, just negate the result from taxable, and then call it as a method reference here. But here I just put it in a lambda expression. I'm kind of wanting to illustrate that I can use method references and lambda expressions interchangeably at will. So here I have the lambda expression, and notice I use the bang operator to negate the is taxable that I got back. And otherwise it behaves the same. I can actually refactor that into a method, and then all I need to do is pass in what is this, what does the compiler treat this as? I said it very early on. What kind of functional interface? This is taxable, line item is taxable, or whatever goes into the filter, I should say. What is that?
Predicate.
Predicate, right? It has a test method. And so if the test method returns true, it passes, and if it returns false, it doesn't pass the filter. So the predicate has that test method. The compiler treats this line item colon is taxable as a predicate. So the lambda expression where I'm bang item is taxable would also be evaluated as a predicate. So what can I do? I can make a factory method down here basically saying, get me the non-taxable predicate and get me the taxable predicate. And then, refactor all these out to use one or the other. Pass in the predicate basically into the method. But otherwise, it works the same. Now I have to modify the order factor because I wanted the order twos, not orders, but that's the only thing there. We test it. Same kind of thing, except now I'm creating order 2 out of the order factor. And here it is. Wow! All that functional work, 1.489. That's hardly any better. And in fact, I'm not even sure, for a different data set, it might have been that the imperative way would have been faster than the functional way. But functional is not, in this case, giving us any speed advantage. Okay? But we're going to change it up a bit. We do get the same results with less code. And so when I mentioned maintainability and readability, definitely the functional way is more readable. The code is more fluent. And performance left unmolested is about equal. So I'm going to change it up just a little bit. I have this slowdown to calculate it. And now I'm going to switch to the parallel string. So I'm going to go off of slides. 1, 2, code. I have to do a change. So I'm using, in this case, the Clojure idea, the version 16 early access, which doesn't really make a big difference. Let's see. What I want is streams. So here's the imperative example. Sorry. I will run this. And there's our 1.63 seconds in the imperative. I run the functional example. And so it's a little slower, even a little 1.485. So in this time, it's a little bit faster, a little slower than the first time I ran it, but a little faster still than the imperative. But I can't actually guarantee that it always would be. So what could I do to make this faster? I kind of had it already. I'm going to use the parallel string. So add concurrency. So let's talk about adding concurrency. So I'm thinking back in Java 7, or let's go even back to Java 5, or 1.02 if you like, because concurrency in Java has always sucked. Even with concurrency libraries, it sucks. And getting it right is really hard to do. And you have to follow lots of prescriptive things to get it right. And so we could synchronize methods, we could synchronize blocks of code on a particular variable, we could do all that. It's just a pain, and and it barely works when I'm talking about, like a 4 CPU, a 4 CPU processor, but what if I'm in a cluster and you know, and I mean, it just is really difficult to get right. And the problem with concurrency is when you get it wrong, it doesn't get wrong at the compiler. And it doesn't get wrong when you run it the first time. And in fact, the rule in concurrency is it only can get wrong at 2 a.m. on a Saturday morning. Because if it gets wrong any other time, you just fix it and go away. And what's really cool about concurrency in the classic Java way is where we tell the computer how to do concurrency. You see that recurring theme with functional? With our classic concurrency libraries, we tell the computer how to do concurrency. Oh, synchronize that method. Oh, synchronize on that variable. We're telling it how to do it, right? And we're waiting on lots and we're doing all this. We're telling the computer how to do it, and the computers are kind of laughing at us. But the real problem with concurrency is when you get that problem, it led to the invention of the coinage of the most famous developer saying in the history of the world. It works on my machine. Because you run exactly the same code and you run it and you don't get that weird, mysterious problem. And it's like, oh, well, it's probably just a bad deploy. So you rebuild and redeploy and it runs and the boss says, oh, thank you. It's 2 in the morning and our customers are angry. And then a week later, it does some other weird thing. It's like, wow, I thought I had fixed that. And then they come to you and what do you say? It worked on my machine. The reason is concurrency never fails in the same spot at the same time. Or if it does, you're the luckiest guy in the world and you should go buy some lottery tickets and the prize gets up. So we're going to do concurrency the Java 8 way. I'm not going to do synchronized. I'm not going to do blocks and locks and all the management. I'm going to go to the order to, and I'm going to put this in presentation mode so that you guys can see exactly what I'm doing. So here's the big change. Remember I had that is string here? I'm going to change that. I didn't want to do any of that. I'm going to change that to say, get me a parallel string. Except I have to spell it parallel with an A. With an A. All right, get me the parallel string. So now I am not telling Java how to do the parallelization. I'm just saying, please give me a parallel string and let me run this. So let's run it. This mode. So I changed that to that, and now I'm going to rerun my functional example. So it was 1.4 seconds. Wow! How's that? And guess what? The parallelization, I'm not going to say it's perfect, but lots of people, when people ask me about concurrency, my standard answer is, I'm not smart enough to do concurrency. But the guys, the Oracle engineers, the formerly Sun engineers, the guys up in Java land at Oracle who really know, the Brian Getzes and these guys, who really know the concurrency stuff, they program the concurrency into the parallel string. So I don't have to worry about me getting it right because I am not nearly smart enough to get it right. They are plenty smart to get it right. And so with a parallel stream, just by doing what I did, you get an automatic 10 threads in a pool that are used. You can customize that, you know, by, and I can't even remember the class name now, but to be able to basically specify your own thread pool size. And so if you're dealing with some big honking 64-way processor or something, you know, how many threads should you have, right? It's like a thread for each CPU and then a couple of extras. You know, when my earlier days in Java, when I first got started in '96, May of '96, I probably did my first concurrency thing around '98 or so. I thought, oh, I'll just give it 100 threads because it must be better than 3. Of course, I was only on a dual-core processor back then. So, 98 of those threads or 96 of those threads will just complete overhead for the thread scheduler. So, so basically it's tied to the number of CPUs. The formula for calculating that you would know in your own environment. But you specify that, and otherwise let the parallel stream library do the work for you. And it will completely parallelize the behavior that you have running in the stream. And I hooked this up with a pretty large data set, just using the 10 threads. And you really do get very close to, a 90% reduction in time, because it's just, if you have like a couple of dual quad-core processors running, you can get really excellent parallelization, and you get it for one line of code change. By the way, when you're in development and you don't care about this, you just leave it as a regular stream. And then when you push it up into QA, you have it configured up there. You have it set up so that your bean that gets you the streams you'll get the streams in a parallel fashion. So that's all we have to do. No synchronizing, no locks, no management, and there you go. So we switched to parallel stream. I told it what I wanted it to do, and in no way told it how to do concurrency. That is the absolute common thread working with functional programming in Java 8. Tell the system what you want it to do. And if you find yourself writing loops and doing all this imperative stuff, you should step back and say, how could this code be done in a more functional way? So I did mention that I do Groovy programming. Groovy has always had functional idioms in it since it was born. And the key thing on Groovy is, and I forgot what version of Groovy, I think it was probably Groovy version 2, it allowed coercion, maybe it's 2.4, it allowed coercion of a Groovy Clojure to appear as a functional interface. Okay? So remember that pick sum example I used before? And I said pick sum, I pass in a collection of values, and then I have a predicate that says how to pick it. So I use the lambda expression. This is the exact same lambda, what looked like a lambda expression, what looks like a lambda expression, except notice I have a curly brace around it, around the whole thing. That's because the curly braces denote closures in Groovy. So this closure here gets evaluated by the joint Groovy Java compiler as a predicate functional interface. And so it works just like with our regular lambda expression. You just add the curly braces. If I don't have any arguments, guess what I don't have to do in Groovy? I don't have to put an empty parentheses there. Worth the price of Groovy just not to have to do it. Now I mentioned that Groovy has functional behavior, so we've always had this method on collections for find all. And in Groovy, if the closure is the last closure is a data as a type, and if the last argument to a method is of type closure, then I don't need the parentheses. I can just show the curly brace here. And I should mention with Groovy, parentheses are optional unless you have no args, then you have to use parentheses. So instead of wrapping this inside a parentheses, I can just say find all, curly brace, close curly brace. So this is a closure. So find all has always been, like this functional thing has always been there. And it works very much like a predicate functional interface. How do you test? I'm a big test guy, and so I feel kind of guilty that I put testing off to the end, but I need to lay all the groundwork for you before we could really talk about testing. How do I test a lambda expression? It's kind of weird looking, so you can't say, evaluate this. The secret to testing a lambda expression is to know that the lambda expression evaluates as a functional interface. How do you test an interface? Oh, well then I have an implementation of the interface, and I I can test it, right? And the lambda happens to be the implementation interface. So what do? I have an array list here, and then I have a predicate that takes an integer type that is called number picker, and I define in my setup method. Now this is not Clojure. I'm not in Groovy anymore. Okay, so this is not Clojure. This is a method. The predicate number picker I just set to the lambda expression that I want to test. And then I have a test, and I assert true, right? Because this is the test. I'm in JUnit 4. And what method do I have on the predicate functional interface? The test method. So I just pass in 101 and say, in this case, I'm trying to find even numbers. 101 is odd. Oh, sorry, I'm trying to find odd numbers. 101 is odd, so this evaluates the true. Assert true. If I test the even number side of it, number picker.test, again, the predicate functional interface, I pass in the 100 as an even number, and I assert that should come out as false. Now, I can test the whole functional aspect of this. I can take all the numbers, string them, filter them using the number picker. And then remember we had the reduce method, we had the find first method. We have another method here called collect. And it says collect, and what I want you to do is use this collectors to produce a new list. In Groovy, this is the equivalent of the collect method on collections, where basically I have a collection of one thing and I want to collect it into another collection, right? Transform it and collect it into another collection. So I'm going to filter out, bring out the odd numbers, let the odd numbers pass through this filter, and I would collect them all into a list, and I'm going to put that in the list called odds. And then I go to assert equals, and then I say, here's what I expect 1, 3, 5, 7, 9 to be in that odds collection. So that's how you can test your lambda expressions. They look weird, but do not skip testing them. Because as you write less code, and you're relying on the compiler to do things, and you're relying on the Java 8 to take care of some things for you, it actually increases your burden to make sure you're really getting what's right. Because that little simple expression could be very misleading, and you could get it slightly wrong. So you want to make sure you have a good unit test for it. In summary, functional interfaces and lambda expressions are cool, but they're just the tip of the iceberg. The real game changer is the way you start thinking about programming. And I'm telling you, when you go back to your shops on tomorrow morning, and you start looking at your code, it's like, oh my gosh, we could eliminate lines and lines of this crap by a few simple elements of functional programming, using lambda expressions, using streams, etc. And then, finally, we can stop telling computers how to do the simple things like how to do a loop, how to do iteration, and just and we can avoid the whole scenario where when we go home at night and turn the lights off, they're all laughing at the stupidity that we did. So that whole expression comes from Neil Ford. That computers laugh at us after we go home because we keep telling them how to do the things they already know how to do really well. That title image of chiseling the lambdas from there. This book is Supermaniums. It is really my Bible in terms of functional programming with Java. It's the best, whatever it is, 150 pages. It's really thin, but it really gets to the point. It walks you through all the stuff I've talked about in more detail. There's a article on Java 8 Lambdas up there. Do go to these no-fuck events. This code, actually, for your code, I'll put a different link up. Sorry, I didn't. It's the same thing, but I put a couple extra examples in here when I'm constructor reference. So you'll want to do that. I did get a question at an earlier job about how to do functional programming with futures. There's an article that I found on that, and I thought I'd include it here. So if I want to do this asynchronously, run through this stream, do the filtering, do the mapping, do the reduction, and call me back when you've got the results, right? Then there's a way to do that using a special feature that was introduced with Java 8 so that you can get a handle of that feature and then come back to it later. And it comes from the stream library, and you come back to it later and say, hey, you know, I'll get a call back that says it's ready, and I say, give me the final result. And that way you don't have to, particularly if you're doing like web stuff, you can return back to the web client right away and then pick it up asynchronously in the future. Any other questions? Any ideas, any thoughts? Someone, who was it that brought that point to me about the breakage? Yeah, so it's like I said, well, we solved the diamond problem because if we put two interfaces, we have two interfaces that have the same default method on them. When I introduce those to my class, the compiler is going to complain and I'm going to have to disambiguate. And that's true. We get into weird cases where my class is in a library that's not being recompiled, and then I introduce two new interfaces with two new conflicting defaults from some other library. So you really do still have a scenario where you could encounter a runtime problem where the runtime discovers that you have ambiguous references to these interfaces, and thus code would get broken and you would have to do something. And if you had a class that didn't even care about those default methods, you would still have to change it, right? So if you added the two defaults, the two interfaces that 1,000 classes are already implementing, if you introduce the ambiguity, you're going to have to resolve the ambiguity. What's the answer to that? Don't introduce the ambiguity. So, you know, it might feel good to like have that one method that has that one meaning, but you will break all your other code if you introduce the ambiguity. And so, just rename the methods. And of course, two methods that take different arguments, though they're named the same, they're really two different methods. So that does not introduce ambiguity. Any questions?
I was wondering if is there a problem using the Apache Spark because it doesn't use MapReduce root file system, and using the JavaFX parallel stream, for example. Did you run into any issues like that, or do you know if you just
I have no idea because I don't use Spark. I can't tell you. I mean, yeah, I would not think that there's a conflict there. But, you know, I would hate to say there isn't, and then you go back and find there is, and then you, like, send me hate email and post bad things about me on Twitter. So, I don't know.
Do you know if these features were implemented just at the language level, or do they have to make any micro changes? VM changes?
Don't know. I mean, I remember a long discussion. Remember Java 8 got delayed because of the security stuff that came up that was unrelated to Java 8. And in that discussion, I remember them saying some of the things that they were trying to do did include bytecode changes, but I'm not exactly sure that those made it into Java 8. The stuff that got kicked out of Java 8 and deferred to Java 9 because of the delay, like Project Jigsaw and stuff like that, where it really does change the underlying structural organization of Java. Those were clearly bytecode changes. So I'm not sure anything that caused a bytecode change made it into Java 8, but I just really don't know.
I was at a presentation in Java 1 and they talked about that a little bit, and I guess the answer is it depends, but I mean, you should just consider that yes, it does. Because if you're using, for example, if you're using something very basic that is just a functional interface, it's behind the scenes being generated. The bytecode itself is going to be a functional interface, right? And some implementation of that interface. But if you start getting really, using some of the really cool things that we've seen,
Like the concurrency stuff, right?
Like the concurrency stuff, the constructor references, method references, and all that.
Well, I guess the question is, could they just reuse old existing bytecode code instructions? Did they have to introduce new ones?
Yeah, I don't, honestly,
There
I don't know.
were new bytecode instructions introduced.
For the stuff related to this functional programming? Okay.
And
So-
a lot of it had to do with performance concerns, making sure that, again, going back to the parallel streams, that you can get the performance that you want out of it.
Yeah, 9 is definitely going to be some big bytecode changes because of the sub-projects that were being molded into that. Other questions on stuff I actually know about? Which I know about a lot of stuff, but I don't know about everything. So, in this Java 8 stuff, if you haven't moved to Java 8 yet, and like if you're on WebSphere and you still have to use Java 1.6 or whatever, I'm sorry. But if you can move to Java 8, there's almost no downside. We use Java 8 in the project that I'm on now, and we don't actually use, because we're using Groovy, we don't have to use any of the Java 8 functional programming things because we already get them. But there's no real cost to it, to you. And they're not fixing bugs on, and 1.7 is no longer supported, right? It's passed into life. 1.6 is passed into life by 3 years or whatever. So if you don't have a reason not to go to Java 8, go to Java 8, and don't just go to your boss and say, can we rewrite all of our code in functional, because he's going to tell you no. If you come to my microservices talk, you'll learn that one of the great advantages of microservices is it allows us to rewrite code with far lower risk than if we have to rewrite some big monolith. So if you get to microservices, it's like, hey, we got this microservice in Java 7 and Spring Boot. Can we do that microservice in Java 8? And it's like, yeah, it's only doing like 2 functions. So go ahead and do that. The risk is really low, right? So microservices give us lots of greenfield advantage. But get to Java 8 and just start introducing it in small places, places where you find really messy code that is very procedural, that if you just switch to functional idioms, the code would be much cleaner, and you could use a parallel stream for better performance. Any other questions? Well, thank you. Thank you for having me here. Go to ArchConf, and we'll see you at one of the NoFots, I'm sure.